Okay, everyone. Today we're gonna do topology, some questions on topology, a book by James Munkres. So this question is, topology, 2.1 exercise. You can just check out the books for the question. So let f be a function from a to b, and let a0 be a subset of a, and b0 is a subset of b. For question A, we're just going to do for question A today. Let x be an element of A0, and suppose, actually I write suppose as SPS just to let you know. So suppose x is not an element of f inverse f A0. Then, by definition, fx is not an element of f A0, and this is a contradiction. And I write contradiction with a lightning mark like this, just to let you know. And this is because x is an element of A0. So this cannot happen. So automatically, x has to be an element of f inverse and f inverse f A0. Now, suppose f is injective. Then let x be an element of f inverse f A0. Then assume, and I write assume as ASS just for, it's not like a swear word, it's just for a comment, just for abbreviation, so don't be alarmed by it. So assume x is not an element of A0, as fx is then element of f A0, then there exists y, which is an element of A0, such that x is not y, and this is due to the fact that x is not an element of A0, and fy is fx by definition. But this is also again a contradiction because f is injective, so this cannot happen. So this gives us the proof that was supposed to be shown in the question. So A is done, and what the heck, I'll just also go for B. So let y be an element of f inverse B0, and then we know that f inverse y will be f inverse B0 as element. And now suppose that y is not B0, y is not an element of B0, and this is also a contradiction because, sorry about the writing, contradiction as then this would mean that f inverse of y is not an element of f inverse of B0, which is a contradiction. And now suppose f is surjective, then then there exists x such that it is an inverse of f inverse y, and this is a subset of f inverse B0, which would mean that y is an element of f inverse B0. And this shows the proof of B. And that's it for today. And once again, this was Anything a Day.